So now we had hinted at this last time also, that these spiral arms, because they are long-lived, they are not material features in the disk. They are a pattern through which stars and gas move in and move out, in at least in the grand design spirals. However, not all spiral galaxies are grand design. Many spiral galaxies are what are called flocculant spirals. And in such flocculant spirals, you have short-lived spiral arms, which can arise from some kind of temporary patches pulled out by the differential rotation of the disk. And these patches may arise from local disk instabilities. So there may be locally some instability that leads to the formation of sort of gravitational sort of high density region, which leads to increased gravity and leads to flow of gas and star formation. So perhaps this is what is happening in flocculant spirals. In flocculant spirals, what is also believed that formation in one place may lead to enhanced star formation in the nearby regions. So this is called as a detonation wave. So what happens is, moment you have one star formation in one place, in the neighborhood, it disrupts things a lot. And it can lead to enhanced pressure, enhanced densities in the neighboring regions, thereby creating conditions suitable for star formation. And so therefore, it's like a firework going off, one firework triggering another. So that is why it's called a detonation wave. So that one detonation, one event of star formation triggers a detonation in a neighboring region. So this is, of course, a good example of a grand design spiral, M51, Whirlpool Galaxy, one of the nearest grand design spirals, and also very, very nicely face on. So you can see the spiral structure almost perfectly. And this, of course, is a nearby companion, but the main galaxy is, of course, here. And this is an example of a flocculant spiral, which I had shown you earlier also. So if you look at this image, look at the PDF and zoom in a little bit, you see that there is some hint of a pattern, okay? But it does not persist on long scales. So here we feel that these are produced by that detonation wave kind of event that we looked at earlier. There is star formation almost everywhere in the disk. There's lots of dust, but there is no evidence of a well-defined spiral arm. Okay. So, is there some way of producing an enhanced density by just changing the position angle of nested elliptical orbits? Okay. So what you see here are, imagine this is one star which is going around in this direction. There is another star which is going around in that ellipse, and so on. So each of these ellipses corresponds to a different star. Okay. And as you can see that these contours or whatever, the orbits come close together at certain positions. And of course, this won't correspond to one star, but many stars well distributed in phase along that ellipse. So at this particular region and in this particular region, in fact, the entire region corresponding to that blue curve that's shown here, you will get an enhanced density of stars. So every star is going around in its own orbit, okay? But remember, the spiral pattern is also rotating. So these orbits are not closed orbits. That whole thing structure is going to be rotating with time. So nothing is closed, but a set of orbits that are in the same plane, but different ellipticities and position angles can create such structures. Yes. Yes. No, this we don't know observationally. Okay, this we just know through theory and simulations. We don't know. We can't measure the rotation observation. So this leads to the main theory that we have for the creation and sustenance of spiral arms, and that is called the density wave theory. And it's due to Lin and Shu. Those of you have heard of this book called The Physical Universe by Frank Shu. That is one of the standard introductory texts. So this is the same Shu. Spiral arms we saw must be persistent. They have to be, because otherwise we won't have seen them everywhere in the universe, in the nearby universe at least. So this density wave theory is what provides an explanation. The arms are density waves propagating in differentially rotating disks. Okay, what is meant by differentially rotating here? The speed of rotation depends on the distance from the center, right? The spiral arm pattern is amplified by resonances between the epicyclic frequencies of the stars, which lead to deviations from circular orbits, and the angular frequency of the spiral pattern. So the spiral pattern is rotating with some angular frequency. In addition to that, each star that is in the disk has what is called as an epicyclic frequency. So think of a situation like this. Suppose you have a star going around in a circular orbit around the center. If I displace it along its circumference, okay, if I displace it along its circumference without changing its distance to the center, is anything going to change? Will it speed up or slow down if I displace it along its circumference? No, right? So if I displace it by, let's say, 10 kiloparsec, if I move it forward, it will remain 10 kiloparsec ahead of where it was originally at all times. Okay, so there is no the epicyclic frequency. If I for a displacement along the tangential or along the tangential direction is zero. It doesn't change anything. But if I displace it in the radial direction, the potential is such that it leads to a kind of rotation about its mean position. More than a rotation, very often it's an oscillation, a radial oscillation with a certain frequency about the mean position. So this is referred to as a epicyclic frequency. Now, for an M-armed spiral, 2-arm, 3-arm, 4-arm spiral, a star at radius r will move through the spiral structure with a frequency of m times omega p, which is the pattern speed. That's the frequency of the rotation of the spiral arms, minus omega r. Okay. So it will, depending if there are more spiral arms, right? M will be higher, and the frequency with which it encounters the spiral arm will also be higher. Of course, omega p has no dependence on r, right? Because it's the whole spiral pattern which turns, so it has to have the same angular frequency. But omega itself, the speed of the stars in the disk, they do have a dependence on r. And these, as we said, stars, each star has a epicyclic frequency, kappa, which in general is a function of r. And it can be shown, and again, this is a long derivation of 4 or 5 pages, so we are not going to go through that. But if you're interested, go to Binney and Tremaine, and you'll find the full derivation. It can be shown that the spiral pattern is maintained only when r of the star lies between values of has a omega r, where omega r is between omega p plus kappa by m and omega p minus kappa by m. Okay, so there is only a certain range of radii in which you can form spiral patterns in a stable way. You can still form spiral patterns, but it will soon get disrupted because the kind of resonances that you need in the frequency of in between the epicyclic frequency, the frequency of the spiral arms, and the frequency of the rotation of stars in the disk at that particular radius are not there. And if they're not there, then the spiral arms get disrupted. So these points, the inner Lindblad resonance is referred to the point where omega r is equal to omega p plus kappa by m. Okay, and the outer Lindblad resonance is omega p minus kappa by m. Now, obviously, this at the inner Lindblad resonance, omega r is going to be higher. So, in terms of frequency, the frequency of rotation in the inner parts of the galaxy are going to be higher. And that we already expected because we said that the rotation curve is flat over a large section of the radius. So if the rotation curve is flat, angular frequency near the center should be higher than the angular frequency outside. So there will be a point where omega p is equal to omega r. Okay, this is referred to as the co-rotation radius. And since this is a positive number and this, I mean, you're putting in a negative number, omega p r is equal to omega p is going to necessarily occur somewhere between the inner and outer Lindblad resonances. Omega r equal to p, and this is referred to as the co-rotation radius or the co-rotation circle. And what is special about that circle? It turns out that by definition, the time taken for the star to complete one circle around the galaxy center is the same as the time taken for the spiral pattern to rotate once. Okay. At that radius, stars which are in the spiral arms, yes, that is correct. So they may still have a kappa frequency, so they may oscillate in the radial direction, okay, but their speed of rotation will remain the same. So stars which are in the spiral arm will remain in the spiral arm. Stars which are outside of the spiral arm will forever remain outside the spiral arm at the co-rotation radius. Stars may stay there, but that doesn't mean gas can't fall in there and new stars can't form. And also stars will stay there. If they are O-type stars and they go supernova, then they're dead. So there's no question of staying inside or outside the spiral arm. Okay. So you can't actually see the co-rotation radius in the image. Okay, but it's there because there, see, it's like this. In the inner part, the stars are moving faster than the spiral arm. In the outer part, they are moving slower than the spiral. At some point, they are moving exactly at the same speed. Okay? But they're also, because of this kappa oscillation epicyclic frequency, they're not stationary. I mean, in terms of their radius also changes slightly. Okay? But they'll come back to their point. It can be in the Z direction also, okay, but it usually, so what we do is we separate the motion as the motion along the tangential direction, which is the overall rotation component, that remains mostly unchanged. Whereas you can think of that epicyclic motion as a sort of motion along the radial direction, but it may go in the Z direction also. So you can have a Z velocity, but you will certainly have a X and Y velocity. And it can be very highly elliptical so that the z velocity is not very high. And how do we know that the z velocity should not be high? Because this disk is mostly thin, right? It cannot go too fast and too far away from the center. It goes in and out quite a bit, but it doesn't go up and down on the disk. Okay. So it turns out that the sun is approximately at the co-rotation radius. Okay. K over sigma for the sun is 1.3. And so the sun makes 1.3 radial oscillations in the time it takes to complete a revolution around the center. Okay. And do you know how long it takes to do one revolution around the center?
250 million.
Sorry?
250 millions.
50 million. No, it's more like 200 million years. Okay, 200 odd, little bit more than that, and which is also quite close to the co-rotation. It's quite close to the period of the spiral arm rotating, and which means that the sun, since it is not exactly at the co-rotation radius but close to it, it is going to pass through the spiral arms relatively slowly. Okay. This density wave theory also explains why the rings of Saturn are persistent. They are long-lived. Okay, for billions of years, the rings have remained stable. Okay, there are lots of papers, so we are not going in that direction. But if you want to look, there is this paper by Hedman et al. 2019, which describes how the rings of Saturn can be explained by this theory. Yeah. I don't know. One has to see that. Whereas finding rings or exoplanets, you mean around other stars, that is very difficult observation. Yeah. Okay. No. It has nothing to, sorry if I confused you. It has absolutely nothing to do with the sun lying near the co-rotation radius. It has only to do with the Saturn and Saturn's gravity and the gravitational field. Yeah. When sun goes through spiral arm, in and out of the spiral arm, the nearest star is still many light years away. So there is no effect whatsoever on the rings of Saturn by it passing through a spiral arm or not. Okay. The only effect could be an indirect one, which people have tried to explore, is does mass extinction event on Earth coincide with passage through spiral arm? Because the probability of a supernova going off nearby is much higher when you are in the spiral arm. If you're outside of spiral arm, its chance of a nearby supernova is very low. So that's the only thing. Did we have any supernova triggered mass extinction of life? But it doesn't affect anything else. So what does the density wave do? The density wave is basically an enhanced density in some region. This enhanced density means higher gravity. Okay? Just a pile up of stars and so on. Objects such as a gas cloud will be attracted to these regions and will drift towards them. And when the gas cloud collides with other gas cloud, stars will be formed. And that is why a lot of the star formation takes place in the disk, and a lot of it takes place in the spiral arms. Many of the stars that are formed in these spiral arms will be faint rate sequence stars just because of the initial mass function, but a few will be bright OB stars. And all stars continue to drift through the region. And the OB stars don't go very far before they explode. And the brightest and bluest of a galaxy's stars will never be far away from a spiral arm in which they were born, because they have very short lifetime, 10 million years. Okay, so it gets formed, an O-type star gets formed or B also, gets formed in the spiral arm, and before it can leave the spiral arm, it explodes. So this is a nice video that I found of what's happening in the spiral arms. So this is in a frame, rotating frame, rotating along with the spiral arms. Okay, so you can see what's happening. If you just try to follow, let me play this again, individual objects, you can see that stars are drifting into the spiral arm over here and coming out on the other side. Similarly, they're going in over here and coming out on the other side. You can see all of these red points over here. What are those things? What kind of stars, or what are those?
Maybe newborn stars.
Sorry?
Newborn stars.
Newborn stars, not really, because remember I told you, if they are newborn stars, they will still be within the spiral arm. Slightly older stars, which have turned into red giants, are what are seen there. Okay, so let's play that again. They're sort of exiting. So when the sun was born, it was probably born in a star cluster in a spiral arm, but then it left. Okay, and then it came back, it passed through eventually, and so on. Huh?
So what is causing these frequencies to arise?
These frequencies are arising because there are the disk is not completely ordered. Okay, it is not as if every star is being given a certain velocity and put on its path, right? It is all, everything has formed out of one pool of rotating disk. Originally, you had a rotating disk of gas, probably, and that disk also has grown with time. So to expect completely ordered structure is unrealistic. And there is dust and gas, which is sort of slowing things down and speeding things up, whatever. So it's just think of it as some rotating fluid. Okay, and within that you have these stars, which are feeling the overall potential of the disk, and they are moving accordingly. So and then because the why this is formed, so we'll come to that. Why are spiral structure formed in the first place? Okay, that is not explained by density wave theory. Okay. What is explained by density wave theory is how star formation happens, or why the arms are persistent, where the arms are formed or can be formed. But can be formed and must form are different things. The theory does not explain why they have formed. There are some limitations of the theory. Okay, so this is M51 in 3 wave bands. ultraviolet, visible and near infrared. And in the ultraviolet, you can see the spiral arms very, very clearly. You can even see the individual OB associations. This is because, of course, the UV light, these stars, hot blue stars, emit strongly in the ultraviolet, and that is why they're very bright. And all the normal stars like the sun, etc., don't emit that much ultraviolet, and therefore they are seen in the visible, but not in the ultraviolet. The near infrared, of course, you see all the low mass stars, so that is much more diffuse. It's much more spread out. Okay, so this is the spiral density wave. Okay, so there are a number of things in this figure which we need to understand. Okay, so first of all, in which direction is the spiral arm rotating in this galaxy? Clockwise or anti-clockwise? Clockwise, that is correct. Okay, and which is rotating faster, the underlying disk or the spiral arm? Underlying disk is rotating faster than the spiral arm. So relative to the underlying disk, which way is the spiral arm rotating? Okay, so think of it this way, that so go to a frame in which the spiral arm is sort of slowly rotating in the anti-clockwise direction. Okay, in that, what is it going to do? It is going to encounter incoming stars and gas, okay, sort of in flowing towards the spiral arm, and they are going to be pulled in faster because of the gravity of the stars in the spiral arm. And so what is going to happen? There's going to be some amount of compression of the gas and dust as it approaches the spiral arm from this side, and the stars are going to form there. Right? And what is going to happen? Of course, the gas and the dust, the gas and the stars are continuing to drift through the spiral arm, and they will appear on the other side. So what is shown as the older stars here are the stars that have not gone supernova, survived, but gone on to the other side. Some of them have turned red giant and become very bright. Those are the things that are going to appear on the other side, of the outer side of the spiral arm. So here they've shown the direction of the disk motion, which is faster than the thing, and the gas in the disk is carried with the stars. We saw yesterday that at any radius, the speed of the gas is roughly the same as the speed of the stars. So at any radius, this is going to be pushed inwards, compressed, star formation happens, the supernovae happen, and some stars exit. Right. Can you say if the sun is in a spiral arm right now? Yes. You know that stellar density in spiral arms, you measure the stellar density in the solar neighborhood and you can figure out, and that has been done. So we are not in a spiral arm right now, we are outside. And what is the motion? So there is 10 kilometer per second component radially inwards, okay, 5 kilometers per second in the direction of the galactic rotation, and 7 kilometers per second northwards out of the plane of the galaxy. So this is our total motion. Total speed, net speed is of the order of maybe 20 kilometers per second, which is not very high. The Earth is going around the sun at 30 kilometers per second. The sun is slowly moving around the center of the Milky Way. It's in the Orion spur between Perseus and Sagittarius arms. Okay, and it passes through a spiral arm for about 10 million years every 100 million years. That is our cadence. Right now we are outside it, but at some point, I don't know when, sometime in the future, we will enter spiral. So here's the summary of the density wave theory. Spiral arms are waves of compression that move around the galaxy and trigger star formation. Star formation will occur whenever the gas clouds are compressed. Stars pass through spiral arms unaffected. That again, because although there is an overdensity, it is not so high that there are any stellar collisions or anything. There is still collisionless system. Everything is just passing. The density wave theory predicts the geometry of the dust lanes and the star formation. Okay, so this is an important point. Where do you expect to see the dust lanes in the spiral arm? On the inner side or on the outer side? Inner side. Inner side, because that is where the gas and the dust is entering the spiral arms. Okay, and it gets slowed down because of the gravity. Theory, so they're all on the inside. The star formation is happening in the main spiral arm, and older stars are exiting on the outside of the spiral. There are two outstanding problems with it. What stimulates the formation of a spiral pattern in the first place? Okay, are these some kind of tidal interactions with an external galaxy that creates a kind of forcing function that causes two arms? So there is no theory doesn't predict whether you should see 2 arms or 3 arms or 4 arms or what. And it also doesn't account for what are called branches and spurs in the spiral arm. So if you look at the spiral arm has some little things sticking out on either side of it, okay, like branches of a tree. Those are the spurs. Those spurs, why they exist, why they should exist, nothing is explained by the density wave theory. Not all, but most. Most stars can also form outside. No, so when so there are many possibilities. One is that it used to have spiral arms, and spiral arms have faded away because all the gas has been used up. Okay, so see, like this, in this whole model, as the spiral arms rotate differentially with respect to the disk, thus gas and dust is collected in one place and the stars are formed. But suppose the process continues for a long time and the gas is all consumed, then you may keep turning the spiral arms, but what will happen? No new stars will be formed. And then the spiral arms will still be there as regions of overdensity, but they will cease to be regions of star formation and you won't see them. In the image, you will stop seeing the spirals. They will fade away. The contrast that you see between the rest of the disk will no longer be there. So that is one. But when we come, this is about really about nearby grand design spirals. In the high redshift universe, there are no spiral arms, there are no density wave theory, nothing. That star formation is happening in a completely independent way. Yeah. Not necessarily, because it may be a completely different mechanism. Okay. Today, if you ask in the Milky Way, where are the stars forming? I would say most of them, they are forming in the spiral arms today. But there are stars in the Milky Way which are 10 billion years old. Did they form in spiral arms? No, because the spiral arms are recent structures. They didn't exist in 5-10 billion years. So not all stars form in today in Milky Way like spiral galaxies, most of the stars are forming in spiral galaxies. That does not mean that all stars in the universe form in spiral. Okay. Even when there is no star formation, there would be spiral arms. So this is what I meant. So this density structure seems to be ubiquitous. It leads to star formation and formation of the creation of prominent spiral arms only when there's sufficient gas. Star formation can propagate in a differentially rotating disk. Example, as supernova shocks compress neighboring molecular clouds. So this is your detonation wave propagating. So this kind of self-propagating star formation may be responsible for the branches and spurs that we see in the spiral arms, or for the disks of flocculant spirals. So maybe in the Milky Way, both processes are happening. There is the density wave driven star formation, and then there is the detonation wave star formation also happening. And so now we have a more complete picture, provided we combine both these theories together. Both are operating and creating spiral arms. So this is again a flocculant spiral galaxy. Lots of star forming regions in the disk, but no obvious spiral pattern. Okay, so now we need to introduce some definitions. So one is called spectral velocity, which is U C ln lambda. Okay, so now what is lambda? Lambda is the observed wavelength of whatever spectral line you are looking at. If you differentiate this, so then you get C delta lambda by lambda, and that will be, of course, if delta lambda by lambda is quite small, this will be the line of sight velocity, right? LOS stands for line of sight. Hence, any light received at spectral velocity U was emitted at spectral velocity U minus V loss. So depending on the observed Doppler shifted velocity will be related to the emitted velocity via this V loss number. The observed galaxy spectrum is the sum of individual spectra of many stars, each with a slightly different V loss. Right? The millions of stars in our galaxy, you measure them, you will get a different line of sight velocity. Line of sight, by the way, implies that it's the radial component of the overall velocity of the star. Speed of light. So the spectrum is going to be Doppler broadened because of this. So suppose you're looking at exactly one spectral line, because every star you're looking, it's all emitting or absorbing that spectral line, because they're slightly different VLOS, the line is going to get Doppler broadened. You can define the LOSVD, line of sight velocity distribution. We will call it F as function of V loss. This distribution, if all stars have identical spectra, okay, then the intensity received at spectral velocity U from a star with velocity V loss is nothing but S U minus V loss. Okay, we have to shift the velocity. Summing over all stars, we can then obtain the galaxy spectrum. So what do we do for every star? We find out what is its V loss. Okay, find out what is its Doppler shifted spectrum, and we are making a simplifying assumption that all stars have the same spectrum. That is incorrect, but we'll come to that later. And if you know the distribution in velocities, you can integrate over all line of sight velocities and get the overall spectrum of the galaxy. This will be the Doppler broadened spectrum of the galaxy. Can we use Fourier transforms to measure FV loss? This integration, what does it look like? Convolution operation, right? Is there any connection between convolution and Fourier transforms? That's correct. So if you take the Fourier transform of both sides, then this GU is something that you can measure with Doppler broadened spectrum, and SU minus V loss is the spectrum of the star. Okay, and now the product of the Fourier transform of F and S will be equal to the Fourier transform of the G function. Right? So you can use, if you know S, you can measure what's the value of U. Sorry, F, knowing G. So in the Fourier space, this becomes a little bit easier to do. So here's what it actually looks like. So this is the spectrum of a single star. Okay, lots of absorption lines are seen in it, and similarly, the below it, right below it, is the spectrum of a galaxy. And what is the main difference between these two spectra? Yeah, lines are broadened in the real galaxy because the Doppler broadening due to different stars with different VLOS is going to give you a broadened spectrum. You can define some properties of the line of sight velocity distribution. You can define a mean, which is just defined in the standard way. And you can define a standard deviation by defining a variance of this kind, VLOS minus the average value of VLOS square multiplied by F VLOS and integrated over all VLOS. Right? Very few spiral galaxies are exactly face on. Even if it is inclined at 10 degrees, 20 degrees, 30 degrees, you can start to use this. Okay. And of course, you can use it for elliptical galaxies where velocities are more, there's no such concept of a face-on elliptical. So how do you actually calculate VLOS, average value of VLOS and sigma LOS? You can define a cross correlation function, right, of the VLOS by just cross correlating the galaxy spectrum and the stellar spectrum. So when VLOS is equal to the average value, what will happen to the cross correlation function? It'll suddenly peak. So imagine let's say you have two delta functions which are offset with each other. If you multiply and add them together, you'll get 0 everywhere. But the moment they line up with each other, you will suddenly get a peak in the cross correlation function. So that is what is happening here. The moment you get VLOS close to the average value, you are going to suddenly pick up, get a good peak. So get it simply by determining the maximum of the cross correlation function. Similarly, one can derive the sigma LOS by measuring the width of the peak in the cross correlation function. Yes, yes. So we have made this thing. This assumes that all stars have the same spectrum. Now, this obviously is a wrong assumption, but need not be totally wrong. Why? Because if you take, let's say, the spectrum, if you take the spectrum of a galaxy, of a quiescent galaxy, not very star forming, then what will it be dominated by? Huh? Yes, so low mass stars in general, right? And low mass stars in general have a spectrum, or they have at least those absorption lines in their spectrum, which are quite similar. They are not drastically different. And there are no emission lines like you see in the O-type stars. Right? All absorption lines. So if you take the solar spectrum and try to pass it off as F-type or K-type spectrum, nobody is going to object. Okay? I mean, theoretically, yes, but in practice, you'll get the same peak of the average value of the VLOS, etc. That cross correlation function. All that will give you reasonable results because the broadly the main absorption lines will be the same. The depth of the absorption will be different in different kinds of stars because their surface temperatures are different. But it will not be a completely different set of lines, or it will not be absorption lines suddenly becoming emission lines. So this is a reasonable assumption, but not very good, but not a total disaster also. But we also assume that the LOSVD is Gaussian. And this assumption is okay for ellipticals, but not otherwise, right? And if the mean velocity and standard deviation are not the same along the line of sight, the overall LOSVD will not be a Gaussian even if each individual distribution is a Gaussian. So this is just stating the mathematical fact that if you have two Gaussians which have different widths and means, if you add them together, the sum is not a Gaussian, right? And this is what is happening in what we've implicitly assumed also here is, which is also a correct assumption, that because the distances between stars are much larger than the diameters of the stars themselves, stars don't hide each other, right? So you can actually get the spectrum of a galaxy simply by adding together the spectrum of its individual stars, right? So each one of them will have a different line of sight velocity. So you can't get an overall Gaussian distributed FLOS because each sum of Gaussians is not a Gaussian. Okay. Now elliptical galaxies. So stars in elliptical galaxies have some ordered motion. For example, there is some sense of the rotation of elliptical galaxy. What that means is, if you try to calculate the net angular momentum of an elliptical galaxy, it is not zero. Okay. It does have some net angular momentum. It is rotating, but very, very slowly. Compared to the net angular momentum of the disk of a spiral galaxy, which is really quite ordered. You can add all the individual star angular momentum vectors together and have a very large net angular momentum. Here, on the other hand, it's much smaller. Therefore, ellipticals are referred to as pressure supported systems, right? So this is analogous to, like, suppose you have a cube with gas inside it. That cube is, or your balloon inside, is pressure supported, right? Because every particle, every atom is moving at its in a different direction at a different speed. That analogy is why this is called as a pressure supported system. To measure kinematics within galaxies, we use absorption lines. Each star emits a spectrum which is Doppler shifted in wavelength according to its motion, and the random distribution of velocities then broadens the spectral lines relative to those of an individual star. And systematic motions, if present, will shift the line centroids. So this is what you would get for elliptical galaxies. So, so these are two things. So there are two galaxies, one on the left and one on the right. What is shown in the bottom panels is the velocity as a function of radius, right? Both of these are elliptical galaxies. And this is the distribution of the velocity dispersion, right? So the velocity dispersion has a very clear peak at the center. So if you want to measure the central velocity dispersion, then you measure this value. This galaxy is somewhat differently behaved. Which of them has a larger rotation? First one, the one on the left. Look at the scale is also different. So this one goes from about -100 to about +100 kilometers per second. Okay, it's almost rotating like a spiral galaxy. The Milky Way will go from -200 something to +200. So this is clearly an elliptical galaxy which is has a rotating disk. If you look at the velocity dispersion here, the velocity is here. This, of course, does not seem to be rotating in a very regular fashion. There is some rotation, and the standard deviation also does not have a clear peak. It's relatively flat, then it goes up, goes down, and so on. Now, over the last 10-15 years or so, it has become clear that originally, before that, people thought that all ellipticals should be like this. Okay? There shouldn't be any obvious structure to the velocities, and they should vary just a little bit about zero. However, it has been found in recent years, primarily driven by observations with integral field spectrographs like Sauron, that elliptical galaxies there are many elliptical galaxies which are called fast rotators. So many elliptical galaxies of this type have now been discovered. The question then being asked is, why did we not discover them earlier? It turns out that there is a slight mass and luminosity bias in this. Earlier, people were looking only at the more luminous galaxies. And it turns out that the more luminous galaxies are like this, and the less luminous ellipticals have kinematics that is much more ordered. See, they could still be rotationally supported. So what is meant by rotationally supported and pressure supported? One, how will you check for a particular galaxy whether it's rotationally supported or pressure supported? You find out its velocity of rotation, and from that you find out what is the expected shape of the galaxy. If it is a very fast rotator, it's going to be highly oblate. Correct. If it's a relatively slow rotator, it is going to be closer to spherical, provided it is rotationally supported. Now, what you do find in a lot of elliptical galaxies is that they're highly elliptical, they're prolate ellipsoids, but they are rotating very slowly. So then you say that's pressure supported, because if it were rotationally supported, it should have been rotating really fast to become so elliptical. And what does it mean to be but why is it elliptical if it is pressure supported? Like if you fill a balloon, it always becomes more or less spherical, right? It doesn't go like always in one direction. So what may be the cause of this? How can you have an elliptical galaxy that is highly oblate, but still not rotationally supported? What else? What will be higher in one direction with respect to the other? Huh? Sorry? No, not observationally, what parameter can you measure that will show you that you did a theoretical calculation and showed that okay, this thing can't be rotationally supported because it is too elliptical and it's rotating very slowly. I measured the velocities. It's not. But what should be different in these galaxies? As a function of direction. There's no gas. It's all velocities of stars in elliptical. Redshift. No, assuming it's not rotating. Consider a case like this, where it's highly oblate. We know it's not rotating, or rotating very, very slowly. There is no way it can be oblate. It should have been spherical. The fact that it is oblate tells you that it is not rotationally supported. So it is pressure supported. But a balloon is also pressure supported, but it's spherical. Why is this oblate? No. Imagine a balloon in which the probability of the molecules inside moving in this direction is different from what it is in this direction. Or the velocities, let's say, are higher in this direction relative to this direction. What will happen to your balloon? It will become like this, right? It will get elongated along the horizontal direction because the velocities are higher. Now, in this case, the net velocity can still be zero. But if the velocity dispersion is higher, then it will get stretched in that direction. It is sometimes said in initial conditions. That is a possibility because once it's higher, it will remain higher. Because what is happening is galaxies stars which are in those orbits, horizontal orbits, are moving faster than stars which are in vertical orbits. They have a higher velocity dispersion. That's all. That you can verify. You measure the velocity dispersion in this direction, measure it in that direction, you'll find it different. So what can be the cause behind it? So it has to do, obviously, it has to do something with initial conditions. Okay, when that galaxy formed, it formed due to so one sort of trivial case we can throw, which is there was one galaxy which had consider a spiral with stars going around like this, right? And that merged with a larger spiral in this direction, okay, which had a lot of velocities in this plane and high velocities. What will happen? These stars will continue with that orbit, but it's not so simple, because when galaxies collide, stars don't collide, but the whole gravitational potential gets altered completely. So stars in general cannot continue like this. So it's not as if the galaxy goes right through and they line up nicely and they form elliptical galaxy. Right? So it'll get totally disrupted, but some memory of the original velocities and angular momentum, etc., gets preserved, right? And that is why you can form more elliptical galaxies. No, it won't, because the orbits are stable. Okay, so they're not closed, but they're stable. So it won't become elliptical. It will remain like that for a long time. On the other hand, if you form a galaxy by merging together 10 small galaxies coming from all directions, then it will be spherical. Then there is no preferred direction. Huh. But there's gravity there. No? That's the second one. See, the gravitational potential is created by the stars themselves, right? It is not some external thing. Unlike your balloon example where the Earth is providing the gravity, for a galaxy, nothing is providing gravity except its constituent stars. So it's an internal dynamics of the system. So there are issues with transmitting angular momentum outwards. So that angular momentum transport is also an issue, right? Suppose the inner region is rotating at a certain angular momentum. You're saying that should somehow get transmitted to the outer regions, it will start rotating, but that is not easy. Gravitationally, if the stuff outside, even if this, like for example, if the sun starts rotating at 10 times the speed, okay, it is going to affect the shape of the sun, but will it affect the rest of the solar system? Yes. Gets changed. Can be possible for low mass galaxies, but much harder to do for high mass galaxies. Yeah. So we'll come back to these topics in the galaxy evolution section of this course. Right now, we're just doing it purely observationally or yes, it will have a higher velocity dispersion in the z-axis. Correct. What do you mean by gradient in the velocity? No, it is much more complicated than that. What we've ignored is that the in the case of a disk, the family of orbits that are possible are all relatively simple. So if you take a disk, you are thinking of something which is going around, let's say, in a tight ellipse and in a circular orbit. Okay? So if imagine taking a spring and just putting it in a circle like this. So that is the orbit of each individual star. So there's some epicyclic motion. The spring is very loose, by the way, because the sun, remember, does only 1.3